Hi, I'm Andrew James, and this is my senior engineering design project, an Internet of Things frost alarm for home gardeners. This project seeks to remedy the issues that gardeners face from unexpected frosts in the spring and fall. When frost is imminent, home gardeners often cover their outdoor crops to prevent damage to the plants. My personal interest in this project began with my parents' home garden in Fairbanks, Alaska, where the growing season is short and unexpected frosts are frequent. The image on this slide is a picture of our home garden. You can see the loops of PVC pipe over the garden beds, which we drape frost blankets over at nights when a frost is likely so that the plants retain extra warmth. By preventing frost damage to crops, the amount of fresh, local food produced is increased, which creates positive externalities for both the gardener and the broader environment, since growing your own food and reducing your reliance on commercial agriculture reduces your environmental footprint. The National Weather Service, a division of NOAA, provides frost warnings for gardeners when meteorological data suggests a frost is likely on a given night, but they can't always predict every frost. When an unexpected frost occurs, gardeners are less likely to have covered their crops, leading to frost damage. These unexpected frosts are particularly likely in the spring, when young, vulnerable plants are being moved out of greenhouses. Market solutions exist that allow commercial farmers to be alerted when an unexpected frost is about to occur, but they're very expensive, starting at around $500. They can be needlessly complex for home gardeners, with multiple sensors at different points in a farm and advanced analytics tools that help them justify their cost to farmers. My proposed solution is for home gardeners is a low-cost open-source kit that can alert gardeners via a mobile app when a frost is incoming. The design requirements for my project are primarily derived from its need to be stationed outdoors. Thus, the outdoor sensing station needs to have components that are rated to work down to at least -10 degrees Celsius, and the project housing needed to be rated to be waterproof. I specified that it should be IP60X waterproof, meaning fully watertight even when submerged in water, to ensure it could stand up to heavy rain and wind conditions. For accuracy, the sensor needs to have less than 0.5 degrees Celsius of error for temperature, and as an outdoor Internet of Things device that may be outside of Wi-Fi range from the house, the microcontroller needs to support Ethernet as an internet connectivity option. Ethernet cables can be up to 100 meters or 300 feet in length, while wireless networks typically extend less than 50 meters inside the house, so running Ethernet cabling is actually a better option for larger gardens for communication. The sensitivity of temperature alerts on the app should be user customizable, and the parts and services used need to be inexpensive and readily available. The entire project should cost less than $200. At a high level, the system is broken into an outdoor Internet of Things endpoint, a cloud service component, and an iPhone app. The outdoor endpoint needs a temperature and humidity sensor, which is connected to a microcontroller that reads the weather data and sends it to a cloud service over the internet. The cloud service, which is an application pipeline hosted by a cloud provider, takes in the weather data from the microcontroller in the communication subsystem, then forwards it to the logic subsystem, where a function records the current climate conditions and detects when a frost is likely by calculating the dew point, then sending a notification if a frost is predicted to the iOS app on the gardener's phone to alert them. Additionally, the gardener can check the current hyperlocal weather conditions at any time by opening the app. When making design decisions about what products and technology to use, I broke the overall system down into 3 categories: the microcontroller, the cloud platform, and the iOS app development platform. The alternatives I picked from for each system are presented here. For the microcontroller, it was important to choose an option that could be configured with minimal hassle, while still being powerful enough to handle cloud communication. The cloud platform needed to be fast to set up and use and offer a free tier with sufficient resources. And the iOS app development language, it was important that it adhere to modern development standards and interoperability with the cloud. In the final design for the endpoint, I chose to use the ESP32 because it's becoming the new standard chip for low-cost connected devices. It's reasonably powerful for a microcontroller with 2 cores, but it doesn't require running an operating system like Linux, which would add unnecessary complexity. The SHT31 temperature and humidity sensor was chosen because it was inexpensive, measured with high accuracy, and came in a waterproof outdoor package. For the cloud platform, I chose to go with Google Cloud with Firebase because of its support for easy mobile app connectivity, and because it had better documentation to get up and running than the alternatives. Finally, for the iOS app, I decided to develop in Swift, Apple's new programming language, and its associated Swift UI library, because of the ease and power of native development compared to cross-platform apps. This state diagram depicts the basic logic implemented on the microcontroller. When the device is plugged in, it starts up and waits until it has successfully connected to the temperature and humidity sensor to continue, then connects to the Ethernet or Wi-Fi, depending on how it is configured, then connects to Google Cloud IoT Core using a low data protocol called MQTT, designed specifically for Internet of Things devices. After that, the device loops once per minute through a cycle of measuring the current climate conditions, publishing them to Google Cloud, and ensuring that they're received, then waiting until the cycle restarts. Not pictured in the state diagram, the loop also contains checks for connectivity with the cloud and with the sensor to ensure good data is being sent, and it can self-correct if there's an outage. The block diagram here shows the logical path through the Google Cloud components. Cloud IoT Core, the MQTT broker, receives connection messages and publications of new weather data from the endpoint, which it acknowledges and then sends on to Google Cloud PubSub. PubSub is a messaging service that communicates between different Google Cloud services. In this case, when it receives a message with weather data, it triggers a Cloud function to run. The Cloud function is a lightweight application that runs on command on Google servers. It receives the weather data and formats it, then stores it in a database called Cloud Firestore. It also sends an alert if the temperature or the calculated dew point are too low and a frost is likely. Firebase, which includes the Cloud Firestore database, is then used for communication with the iOS app. When the app is first launched, the user is prompted to log in, which sends an authentication token to Firebase. Firebase sends back confirmation so that the app can begin communication. While the app is open, new weather data is pushed from the database every time it's updated. The user can set a custom alert notification threshold, i.e. what temperature do they want to be notified at no matter what, in the app, which is sent on to Firebase. When the Cloud function detects temperature is lower than that set threshold, or a dew point below freezing, it sends a notification to the app via Firebase so that Gardener is warned of the incoming frost. These are a few mock-ups of the app design created in Adobe XD before the app was developed. The far left screen is the first screen a user sees when opening the app for the first time, prompting them to log in and sending an authentication token to Firebase. Once they're signed in, they are prompted to enter the ID of their device and its physical location, pictured in the second image. Once this data is entered, they progress to the main app screen, the third image in this slide. It gives them the current hyperlocal weather data pushed from Firestore. Originally, I intended to also have weather data from the Open Weather Map API implemented, but this took too much time and cost too much money. So it's just the local weather data in the final product. If they tap the settings link, they're brought to the fourth page, which allows them to choose between Celsius and Fahrenheit and set the temperature threshold to receive notifications at. They can also change devices or log out of the app. I finished the programming for the ESP32 endpoint to work with either Ethernet or Wi-Fi and continually report data to the cloud. I completed a week-long test and got nearly 100% uptime, with only 1 minute per day when the device was unable to communicate due to my router refreshing its DHCP server. The device was able to recover from this successfully. The outdoor housing, pictured in the photos, has been assembled with holes drilled in the bottom to accommodate the temperature sensor, which you see sticking out, along with Ethernet. Here's a quick demo of my app running on a simulator. It also runs on my phone, but this was simple to record. As you can see, the sign-in with Google process is very simple. The settings screen has been slightly modified to allow for more easily changing the connected endpoint based on its ID, as shown here, but otherwise functions exactly as expected. Note coming up that the temperature data instantly syncs from the cloud, as you just saw. There's no need for refreshing from the app, and the same is true for the settings. Everything is instantly synced back and forth between the cloud and the app. The plan for this app is to release it as open source. The code for both the iOS app, Google Cloud Component, and the ESP32 is all on my GitHub along with configuration info, and I'll be posting full assembly and setup instructions as I have the time. I think it'll be a good project for gardeners who like DIY projects, especially those who are interested in electronics and may already have some of the components lying around. Other developers can also build on it and modify it. I would personally like to see a physical alarm rather than just a push notification on a mobile app That might be something I try this summer. If you want to see more of the technical details or implement it for yourself when it's complete, the project is on my GitHub, and I'd be happy to have others make use of it. Finally, here are the references for this presentation. Thanks for watching.